Good afternoon, everybody. Welcome back after Thanksgiving break. Hope everybody had a nice couple of days off. I took a couple of days off entirely, and I'm just getting back into the swing of things. And boy, after taking a little bit of time off, it sure hits me like a brick to get back into trying to juggle all these different things. And I know you guys are in the same boat, or possibly even worse with all the classes you're taking. So all right, let's see. Who do we have online? Who are we waiting for? See, I'm showing 6 minus me, so that's 5 people. I know that Joe said he would be late. Right, okay. All right, so let's go ahead and jump in. This is the last week of classes. So we have today's meeting, Thursday's meeting, and then we're done. So office hours tomorrow afternoon on campus, and then on Thursday morning. As a reminder, there isn't a final exam. So the only exam that we have is the one you guys took a couple of weeks ago. So you don't have to plan around anything else for the class as far as exams are concerned. Here's a summary of our homework. And I've decided that we just didn't cover enough material to justify homeworks number 10 or 11. So I'm going to strike those. And so homework number 9 will be the last homework that we're going to submit for the semester. That's due tomorrow at 5 p.m. I've been pretty lax with submittals so far this semester. If you're going to be a day late with that, it's not going to kill me any. But one thing is, I won't accept any homework after Friday at 5. That'll be the last time I accept anything. My intent is to go through and assign grades pretty quickly in this class, knowing that we don't have a final exam. All right, so with that, let's take a look at the exam that you guys did complete a couple of weeks ago. You should have noticed that I assigned grades this morning, and then the way that I did that is I downloaded the PDFs to my computer and then marked them up on my computer with a pen and then uploaded the PDFs again. So this was the first problem. It was a goofy truss. I'm not sure, what that would be used for in the real world, but analytically speaking, it's relatively simple and straightforward. So we got what? 1, 2, 3, 4 nodes, 1, 2, 3, 4, 5 members. So it's not dissimilar from the trusses that we worked as example problems. I gave you a member stiffness matrix for member E, and I gave you the completely assembled unrestrained stiffness matrix to kind of give you guys a little bit of help. If you go through and work out the displacements that I asked for, then those are given here. In fact, that's all the displacements, because at nodes 1 and 3, there aren't any displacements given that those are restrained nodes. The force in member E is 19.53 kips. So a couple of things to note in looking through your solutions. Let me sound like an ass for a minute. Nobody should have gotten this wrong, because everybody can go into visual analysis and calculate the right answer. Couple of people still got it wrong. The displacements I calculated out to 4 significant figures. I had several people submit, like 0.0017, or I think there was even one person who submitted 0.002 as the displacement for delta 3. Not okay. You got to go a little bit further than that in order to let me know that you've done some accuracy. I actually had a couple of people get the force in member E incorrect, and that's something you guys could check using statics and a page, not even a page, a few lines of hand calculations. So again, not to sound like an ass, but you have 3-4 days on a take-home exam. That's probably not something you should miss. That's the slam dunk that goes off the rim and out of bounds, right? Anyways. Second problem, I ask you to determine the load matrix that is associated with this beam. And I didn't ask you to actually do the matrix analysis, though I had a couple of people that submitted a full matrix analysis of the problem. And if you go through and use the equivalent end actions, then this is the load matrix you should get. I calculated it out using kip and feet units, and then I realized that most of you are going to do it in kip inch units because you're used to using consistent units. So those are the results that you should get for that. Most of the errors that I saw in this this were associated to using incorrect units or possibly sign errors. A couple of people had signs wrong on these problems. The third problem was the same as the second problem, except now I ask you to go in and do an analysis of this beam in SAP 2000 and give me beam deflections and bending moment diagrams. So if we look at those results, this is what we got out of SAP 2000. So I think most of the students in the class, and there's only 7 of you, so I think that's like 5 out of 7, got the right bending moment diagram, shear force diagram. But we had a lot of errors when it came to the displacements. The crux of this problem is that in order to get accurate displacements or deflections out of a beam problem like this, you have to have nodes along the length of the beam. If you don't put nodes along the length of the beam, SAP 2000 uses a cubic approximation for the deformed shape. And really, when you have a member that's subjected to a uniform load like this, then that cubic approximation is insufficient. It doesn't give you the most accuracy. So in order to get accurate deflections, you need to have at least some nodes along the length of the beam. At a minimum, if you put nodes under the point loads, that will give you a lot more accurate results than having no nodes at all. And then just to investigate the extreme, I went in and put nodes every 6 inches, which is probably more than what is really needed for most design work. But I suspect that would give me the an answer that would converge if I kept dropping down the nodal location. So if you got 0.0957 and 0.04004, then you got 15 out of 25 points. I subtracted 10 points for not putting those extra nodes in. And then the last problem was an expansion of the second and the third problems. Let's extend the uniform load over the full length of the beam. We'll have the two static point loads, but then I wanted you to add in a moving load as well. And so there's a third point load that's not shown on here that could be anywhere along the length of the beam. And so that triggers the idea of a moving load, which takes us from a shear force diagram, bending moment diagram, to a shear force envelope and bending moment envelope. And so if you go through and use the moving load correctly and use a linear add to get your results, then these are the results you would get. Basically a maximum positive moment of 104 kip feet, or a maximum negative moment of 110 kip feet. However, if you use a range add instead, then you can get a larger bending moment on the order of 115 kip feet in the positive moment range. And so that results, if you omit the live load from one span, that makes the live load in the other span that much higher. And so this was, I think I subtracted off 10 points for using a linear add instead of a range add. Some of you who screwed up definition of the moving loads and things like that lost even more points. So let's see, statistics on this exam aren't that meaningful. There's only 7 samples. The high was a 90, the low was a 59, the average was a 75. There were people, there was at least one person who got each problem correct. Nobody got all the problems correct, but somebody got 100, all the points possible on each of the problems. Let me go through and do another statistic here. I got the spreadsheet open on the other computer. Oops. So statistically speaking, the last problem was the most challenging. On average, students earned 60% of 25 points. The third problem was the next most challenging. On average, students earned 63% of 25 points. And then problem 2, 85% of 20 points. And then problem number 1 was the easiest, 92% of 30 points. So it gives you a little bit of statistics there. Right. So then the question is, well, gee, I only have one exam. I didn't do great on this exam. What does that do to my grade? I never published a syllabus for the course. I kind of regret that. I was waiting for some guidance on teaching assistants. That never came, and I never came back and closed the loop. However, in going back and looking through old material, during the first class session, I published this: 60% exams, 40% homework. So I'll go with that. And if the homework grades stay on track, then that will give us basically mostly A's and B's for the class. Obviously, I'm not at liberty to discuss too many details here, particularly given that this is a recorded session. It's going to be posted online. So, for those students who earned a 59 or 60, that's not necessarily the end, a condemnation to an F or anything like that. So homework grades have been largely positive. As long as you submit an honest effort, then you get full points on them. All right. With that, I'll entertain questions, but bear in mind we are recorded, and you probably shouldn't ask anything specific because we would violate FERPA policies and things like that. If you have a specific question about, gee, why didn't I earn more points on this problem, then I'd urge you to reach out to me during office hours instead. All right. So, with that, if you guys want to catch up with me tomorrow at 1 or on Thursday morning at 8:30 and ask specific questions, that would be fine. I probably won't post a full copy of the solution to Canvas, but you can go back and review the work that you've done and review this recording when I post it online and have a look at that. I'll try and post that later this evening so you can take a look at it before office hours tomorrow and Thursday. All right, so then moving forward, that takes us to today's agenda. We'd started talking about AISC direct analysis method, or AISC methods of analysis in our last lecture. I wanted to pick up on that today and finish that up. And then looking ahead, we have but one more class on Thursday, and my goal there was to introduce the idea of a staged construction analysis in class on Thursday. That's something that's available in SAP 2000, but not visual analysis. And this is probably a specific enough feature that you're going to find it in relatively few packages. And so SAP is the only one that I know of, but I'm sure somebody else offers something similar to that. All right. So that being said, let's go ahead and go back to the direct analysis discussion and pick up where we left off on Tuesday of last week. All right, so to kind of bring us in and pick up where we left off, but give us a little bit of a reminder, AISC offers a number of different methods for analysis, and this whole conversation is born out of as an extension of our conversation on second order analyses. We have P little delta, P big delta analyses, and then that leads us into the type of analyses that are required for the design of steel structures. And so in AISC specification, they allow us to do the direct analysis method. They allow us to use an effective length method. They allow us to use a first order analysis method and a simplified method that appears in the manual, but not in the specification. And so when we look at how these different methods shake out, the direct analysis method is the most robust of the four options that are available to us. It can be applied to any structure. And the reward for jumping through the extra hoops that are required for a direct analysis is that you can design all of the members in the structure for an effective length factor of 1. The effective length method and the first order analysis methods are permitted when the second order effects are not large. And in some cases, if you have a very lightly loaded structure, you can actually use the effective length method and still use effective length factors equal to 1. I'll get to that in a few minutes. The first order analysis method is when you have relatively lightly loaded columns and when the second order effects are small. And then the simplified method is just a dumbed down version or a watered down version of the effective length method. And so if you look at the progression here, the analyses are more sophisticated and more challenging at the top, but you get a better reward for that by being able to use K factors equal to 1. And you get a more conservative analysis as you move to the bottom. If you have members that are lightly loaded, for example, then the implications of having second order effects become less severe. Right. So then we, at the very end of the lecture, we introduced the idea of a notional load, and a notional load is a type of a load that is not meant to explicitly model something that's going to be acting on the structure. So when we go in and look at our models, we've been modeling things like live loads and dead loads, moving truck loads, for example, snow loads and wind and things like that. Each one of those are representative of a physical phenomena, something that's physically acting on the structure. But a notional load is a load that's meant to capture the effects of something that we don't want to model explicitly. And so examples of those are things like geometric imperfections, unsymmetrical pattern loads, temperature gradients, foundation settlements, column shortening, and things like that. And so the idea here is that if we were to try and capture, say, geometric imperfections, if we were going to put in all the different possible permutations of having a building a little bit out of plumb, that would become very challenging from a practical point of view. Is it out of plumb to the left? Is it out of plumb to the right? Is it out of plumb in this direction, out of plumb in that direction? What if it's out of plumb in two directions at the same time? And it just becomes almost an unworkable problem if you ever want to make any money as a structural designer. So you can use notional loads instead. So you can model the structure as perfectly plumb, but then put a horizontal load on it that's going to give you axial forces, shear forces, bending moments in the members that would be similar to those axial forces, shear forces, and bending moments you would get out of an imperfect structure. So in AISC, notional loads are generally defined as lateral loads that act at each level in the structure. They're generally some percentage of the gravity loads that are acting on each one of the levels. And so notional loads on the order of 0.2% or 0.1% are typical. So if you had, let's see, 1,000 kips of dead load acting at one level, then multiply that by 0.02, and what would you get? 5 kips of lateral load out of that. And so that would be a typical number. All right, so now that we know what a notional load is, let's dive into some of the requirements that are included for the different methods of analysis in the AISC specification. So we'll start off with the effective length method. The use of the effective length method is limited to the following conditions. The structure supports gravity loads primarily through nominally vertical columns, walls, and frames. Now, that might sound like a no-brainer. Most of our building type structures have columns that are roughly vertical. They're specified as vertical at the beginning, but that's not always a given. And you can find some examples of that on the University of Cincinnati campus. If you look across Nippert Field towards the athletic center, the building that I call the Amoeba Center, the Amoeba building, then that has a grid work of columns that are battered or inclined by about 30 degrees. So for a structure like that, those columns are not nominally vertical, so you would not be able to use the effective length method. Another example might be the Vance Center for Molecular Science over on East Campus. That structure has some walls that are out of plumb by by design, and so the columns in that structure probably aren't vertical either. So that would be another case where you weren't permitted to use the effective length method of analysis. The ratio of the maximum second order drift to maximum first order drift shall be less than or equal to 1.5. And 1.5, I'm sorry, delta first and delta second are both determined for LRFD load combinations or 1.6 times the ASD load combinations. That brings up something. Let me go back to that slide. There was a vigorous discussion at the AISC meetings last week about the inclusion of allowable stress design. That's an issue when we look at the ASD load combinations that are in ASCE 7 versus the LRFD load combinations that are in ASCE 7. When we start to compare the results of designs using LRFD to those using ASD, they're not always comparable. And so AISC right now is really grappling with how to deal with that inequality, the lack of agreement between the two methods. Now, from a fundamental point of view, you shouldn't necessarily get the same design. They're based on two different philosophies. So if you expect to get exactly the same answer, then you're probably don't have a great grasp of the fundamentals of design anyways. But So this factor of 1.6 crops up quite a bit. Sometimes you see a factor of 3/2 or 1.5. You can multiply the ASD loads by 1.5 to get approximately the same LRFD loads. And the options that were discussed a couple weeks ago in Chicago were a little bit different than that. There's a factor that's applied to all the load combinations except for load combination number 1, which is just dead load. So anyways, I thought that was interesting, and it came to my mind when I read that. So when we talk about the required strengths shall be determined from an analysis that includes P little delta and P big delta effects. And in the case of the effective length method, there's no reduction in stiffness required in our model. EI and EA are permitted to be used at their nominal values for all members. What we'll find is that when we get to the direct analysis method, you have to use a reduced value of EI and EA to account for partial yielding. Things like inelastic flexural buckling of columns, plasticity in beams when they get close to their design flexural capacity, things like that. Notional loads must be used to represent geometric imperfections. The notional loads are 0.2% of the gravity loads applied to the gravity only load combinations. So if we go through and look at our load combinations 1 and 2 are gravity only. There is one version of load combination number 3 that includes wind. So part of load combination 3 is gravity only. The other part is includes a lateral load. And then load combinations 4 and 5 deal with wind, so they're exempt. Load combinations 6 and 7 deal with seismic, so those are exempt as well. All right, the available strengths, if you were to go through and calculate how much capacity a steel beam has or steel column has, are calculated using the appropriate chapters from the AISC specification. And the effective length factor K for all the members, it's taken as 1 for brace frame systems, or you take K from your alignment charts for moment frame systems, except that if you have a relatively low value of delta second over delta first, if delta second over delta first is less than 1.1, then you may take K equal to 1 for all of the members. And so this is really nice. If the second order effects aren't that large, then just take K equal to 1 everywhere. And so that's saves a lot of time in calculating the available strengths of the members. And so if you look at the details behind this a little bit, the language of Chapter C and Appendix 7 gets to be a little bit cumbersome, but basically here it says in brace frame systems, blah, 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 the effective length factor shall be taken as 1 unless a rational analysis indicates that a lower value is appropriate. So that opens the door to using alignment charts for brace frame systems, and you could potentially end up with an effective length factor less than 1.0, but most practicing engineers will probably take 1.0 and run with that because it saves a lot of time in their calculations. Then looking a little bit more at the detailed language associated with moment frames, you see similar language there. Effective length factor shall be determined from a side sway buckling analysis, which means using alignment charts. And there's your value of 1.0 if delta second over delta first is less than 1.1. So there are flow charts that are helpful. And so this is one flow chart here that goes along with our effective length method. If delta second over delta first is larger than 1.5, then you can't use it. You have to use a direct analysis method. If it is less than 1.5, then you apply notional loads to the gravity only load combinations where the notional loads are equal to 0.002 times y sub I. So what that means is that you're going to have a notional load associated with dead. You're going to have a notional load associated with live. You'll have a notional load associated with snow, notional load associated with the roof live load, rain load as well. So you're going to have one notional load at each level that's associated with each of the gravity loads that are assigned. And then you include those in the load combinations multiplied by a factor of 1.2 or 1.6 or whatever is appropriate for the given load. Okay, then after you have all those loads applied, you can come down and use a second order analysis. We'll almost always go in this direction in our discussion because we're talking about finite element analyses. The approximate first order analysis method is becoming rather antiquated now anyways. And so after you have your moments and axial forces, M sub u and P sub u from your second order analysis, you go through and compare that to the available strengths. And if delta second over delta first is less than 1.1, you're allowed to take K equal to 1. Otherwise, you come down and use the alignment charts for your K factors. All right. So having discussed that, let's discuss the direct analysis method of design now. So this is the most sophisticated of the analysis methods, the one that can be applied to any structure. Excuse me. Okay, now let me go ahead and read this slide verbatim. For the direct analysis method of design, the available strengths of members and connections shall be included, or shall be calculated rather, in accordance with the provisions of the appropriate chapters and no further consideration of structural stability. So what that means is that the effective length factor can be taken, or in the words there, shall be taken as unity unless a smaller value can be justified by rational analysis. So that's the real benefit of the direct analysis method. You invest a little bit more time in the analysis of the structure, and you can save that time in the calculation of the available strengths of the members. So when we talk about what has to be included in our analysis, it has to include these 5 items. And if you talk to some of the folks that are in the committees of AISC, they would refer to these as the big 5 sources of instability. And so item number 1, the flexural, shear, and axial deformations of the members and all other deformations that contribute to the displacement of the structure have to be included in the model. So we include flexural deformations and axial deformations. Those are included in even visual analysis, right? SAP 2000 by default includes shear deformations, and visual analysis will include them as well if we ask it to, but we have to be a little bit tricky in doing that. Second order effects have to be included, both P big delta and P little delta. So that involves changing the analysis definitions in SAP 2000, possibly using automatic meshing. So we have multiple nodes along the length of the member, et cetera, et cetera. Geometric imperfections have to be included. That doesn't necessarily mean that you have to model the structure out of plumb. There are other methods of including geometric imperfections, but you have to use something to give you geometric imperfections in your model. Stiffness reductions due to inelasticity, and then uncertainties in the stiffness and the strength. So this is a slide that I like to include to reinforce a notion that we've already discussed, and that's the idea that you can't use load combinations as they are defined in SAP 2000 with a second order analysis. If you take a load combination in SAP 2000, you're actually combining the results of different analyses. And in order to get accurate second order results, you have to have all of the loads on the structure for that analysis. So if you're going to use load factors, they have to be defined in what we would call a load case in SAP 2000 and not in a load combination. And so that's an idea that's reinforced here, that superposition holds when we're doing a linear first order elastic analysis, but superposition does not hold when we're doing a second order inelastic. All right. When we talk about the analysis, considering all of the deformations, connection deformations need to be included as well. So we often lump our connections into one of 2 bins. We either say that they're fully rigid FR framing, like the welded connection that's shown there on the left. Sometimes we say that they're simple framing, or simply supported beams is where that comes from. So we have a pin hypothesized between the end of the beam and the column that it frames into. But in actuality, a lot of the connections are somewhere in between. They're not quite fully rigid, but they're not quite simple either. And so what AISC would have us do is categorize them as either FR, simple, or PR. And when we model a partially rigid or partially restrained connection, we're supposed to use some type of a spring model or something like that. SAP 2000 allows us to do that. We can put in a rotational stiffness to account for PR connections. Okay, item number 2, we have to include P big delta, P little delta analysis. It doesn't say that we have to do a rigorous analysis. We don't necessarily have to use a Newton-Raphson approach or something like that. We can use an approximate analysis. But here's where the benchmark problems that are in the AISC manual come into play. You have to validate your software using those benchmark problems before you can move forward using a p-delta analysis. So that's what's covered there. You're also allowed to use an approximate analysis, and this is the B1 factor that you'll find in Appendix 8 to the AISC specification. Okay, it's permissible to neglect p little delta analyses, or sorry, p little delta effects on the structure when the following conditions are satisfied. When the structure supports gravity loads through nominally vertical columns, when the ratio of delta second over delta first is less than 1.7, and when no more than 1/3 of the total gravity load on the structure is supported by columns that are part of the moment resisting frames, then you can ignore p little delta effects. But my 2 cents on this is that if you're including second order effects, all you have to do is auto mesh the structure in SAP 2000 and you're automatically accounting for p little delta effects anyways. So I don't see this as being a particularly large hurdle. Maybe if you're using a package like visual analysis where automatic meshing is not as easy, then capturing p little delta effects might be more challenging, and this might be a nice way of accommodating that in a package that's less sophisticated than SAP 2000. Okay, item number 3, the analysis shall consider all gravity and other applied loads that may influence the stability of the structure. And it's important to include gravity loads in the analysis. There's a temptation, or maybe if you go back 10, 20, 30 years in structural engineering, you might have one model of the structure that you use for gravity loads, but then have a separate analysis for lateral loads. You can't do that. You have to go back and you have to have all of the loads on the structure at the same time. And this goes back to, the idea that we can't use superposition of the results of individual analyses. We have to have all the loads on the structure at the same time. So when we talk about geometric imperfections, that's covered in section C2.2. AISC gives us 2 different options for that. We can either use direct modeling of the imperfections, or we can use notional loads to account for the anticipated imperfections. And so if you take a look at this slide here, these are the 2 options. So here's a structure, I don't know, what is it, a 20-story building. I just put together a quick model. And so option 1, or option A on the left, is to actually generate your model with the nodes out of plumb one direction or another. And so this would be a geometrically imperfect structure on the left. And the option on the right is to go in and include notional loads that would basically result in similar bending moments, shear forces, and axial forces that you would get from the model on the left. So then the next question is, well, how far out of plumb do they have to be? Well, the initial out of straightness is addressed, not addressed in this. It's accounted for in the compression member design. But when you talk about the initial imperfections, then the structure should be analyzed with joints displaced from their nominal locations. The magnitude of that initial displacement shall be the maximum amount considered during design, and the pattern of initial displacements shall be such that it provides the greatest destabilizing effect. I keep saying initially, tripping over my own tongue. So what you can do is go to the AISC Code of Standard Practice, which includes reference to an initial out of plumbness of about 1/500. You can go to other governing requirements if there are some. Maybe you're designing for like the LA building code or the New York City building code, and they might have something different there, so you're allowed to use that. Or maybe the initial imperfections are known. If you're doing an analysis of an existing structure, maybe you're considering a structure that was erected 30 years ago and they're redesigning it or adding on to it or renovating it or something like that, then you can go out and take shots with a total station or whatever and use the actual imperfections. That's permitted as well. When you consider the initial displacements, you're supposed to consider displacements due to loading, anticipated buckling modes, and you should consider modeling of those imperfections, both patterned together and individually. And so when you look at different modes of buckling, the first mode of buckling for this structure, the first mode of vibration, is shown here on the left. The second mode of vibration shown in the middle, and then the third mode of vibration is shown on the right. And so when you're dealing with a package like SAP 2000, you can pattern these together and have it displace those nodes. But my 2 cents again on this is that I think most practicing engineers are going to use the notional load approach instead of modeling these initial imperfections. It would have to be something rather outside the box in order to justify the amount of time that would be required to do this, particularly if you're going to a 3D type of analysis. If you're going to go into ETABS and do a 3D model of the structure instead of a 2D model, then this gets to be a Pandora's box, something that you could spend a lot of time on. Right. Let's see. In the analysis of structures that support gravity loads, primarily through nominal where delta second over delta first is less than 1.7, it is permissible to include imperfections only in the analysis for gravity only load combinations and not in the analysis for load combinations that include lateral loads. That's important because if you include the initial imperfections and then you add wind load on top of it, and then the two are additive to each other. So if the second order effects aren't large, if delta second over delta first is less than 1.7, then you don't need to include the imperfections in the load combinations 4, 5, 6, and 7, where you have wind and seismic. There's also a star there too, delta second star and delta first star. They're not the same as delta second and delta first. The difference is that delta second star is calculated using a reduced stiffness, and delta first star is calculated using a reduced stiffness. I'll come back to that in a moment when we get to that. Here's how we calculate here's how we would account for geometric imperfections using notional loads. The notional load shall be applied to the model based on its nominal geometry and is applicable to all types of structures. But let's see here. The notional load is equal to 0.2% of y sub I, where y sub I is the gravity load applied. It shall be additive to the other loads and in all load combinations, not just the gravity only load combinations. When it says additive, what that means is if the wind load is pointing from left to right, then the notional load should also point to left to right so that it creates a worst case effect. If the wind load is pointing from right to left, then the notional load should point in the same direction as that wind load. Right. And so here's another caveat that when delta second star over delta first star is less than 1.7, then the notional loads can be applied to the gravity only load combinations. All right. The notional load shall be distributed over the level the same manner as the gravity loads. So our temptation would be to go in and put the notional loads and apply them only at the edge of the structure. We'll go back here to slide 13. I'm showing one notional load there. But if there's actually columns in the structure like this, then really you're supposed to break that notional load down and distribute it over the plan of each of the levels in the same proportion that the gravity loads would be. So if the interior columns in this case are each carrying say 40% of the gravity loads, then 40% of the notional load should be applied at that location. If you have a diaphragm constraint imposed, then it probably doesn't make too much difference. But if you're dealing with a structure that has a flexible diaphragm, then that could be important. Back to where we were with that slide. We got that was slide number 37. Slide number 38. The load coefficient of 0.002 on our notional loads is based on an initial out of plumbness of 1/500. If you want to use a smaller or a larger value of the initial out of plumbness, you're allowed to adjust those notional loads appropriately. So that's permitted in those cases. Now here's a reference to the adjustment to stiffness. I mentioned that in a lot of cases, we're going to have columns that are governed by inelastic flexural buckling or beams that are governed by plastic moment. In those cases, some of the material is yielding, so we end up with a reduced stiffness. So what this says is that a factor of 0.8 shall be applied to all stiffnesses that are considered to contribute to the stability of the structure. So basically, we go back to our classification of lateral force resisting systems versus gravity systems. If you put a horizontal force on the structure and you develop a bending moment or an axial force in that member, then that member is part of the lateral force resisting system, and its stiffness should be multiplied by a factor of 0.8. So that can be challenging to go in and apply this to some members, but not all members. So AISC recognizes that and says that it's permissible to apply this reduction factor to all of the members that are in the structure. So you can just go in and modify the value of E for all the members that are made out of steel, or you could go in and select all the members and use a property modifier of 0.8 on E or a property modifier of 0.8 on A and I, and be done with it. Okay, applying to the there's a user note that talks about some of the challenges if you apply the stiffness reduction factor to some members but not others, then that can be problematic in the model of the structure. There's Joe. Hi, Joe. All right, you're allowed to include or you're required to include an additional factor rather for the flexural stiffnesses based on the amount of loading that's present in the columns. If you have lightly loaded columns, then the stiffness reduction factor is taken as 1.0. If you have heavily loaded columns, then you're supposed to calculate a stiffness reduction factor using this equation, C2-2B. This is challenging, though, because the model definition for the structure depends on the amount of force that's in the member. And so it's one of those chicken and egg problems, right? You can't calculate tau until you know P sub U. You can't calculate P sub U until you know tau. So there's a short circuit method that's applied here. You're allowed to use a value that is based on another value of 0.8. So you're allowed to use 0.8 times tau sub B. And if you want to, you're allowed to, take tau sub B as a lower bound, I think of 0.8 again. So you end up with what, 0.64 times E sub I, or times E times I. Right. And then where you have other materials in there, you would refer to the governing codes and specifications on how to account for their stiffness reduction. So if you have a structure that's made out of both steel and concrete, you would go into the ACI specification on how to model the beams and columns there. And remember, we use different property modifiers to account for cracking in concrete members. And so we would need to account for that as well. All right, so in summary, with the direct analysis method, it's applicable to all structures. There's no restrictions. We design all members using K equal to 1.0. We're required to do second order P delta and P delta analyses, though a second order P little delta analysis can be neglected in some cases. The model must include connection deformations. That includes, FR, PR, or simple framing. And so when you do that, then, rigid end offsets and things like that come into play. I don't think I mentioned that a few slides ago when we touched on that, but you could use rigid end offsets and you can have the offset, offset stiffness factor that we discussed for SAP 2000. You have to include for the initial imperfections. Notional loads are typically used, but you're allowed to use direct modeling of initial out of plumbness and things like that. And you have stiffness reduction that's required, where you reduce the stiffness of all lateral force resisting system members by 20%. All right, so if we apply a flow chart here, then if we have a case where delta second over delta first is less than 1.7, then all the gravity load combinations have to include our notional loads. If it's greater than that, then all of the load combinations have to include the notional loads. We have a value of EA star and EI star that include stiffness reduction. And then after we have our model defined, if we have P sub U less than 0.5 times P sub Y, then tau is equal to 1. Otherwise, we calculate tau using this equation, we're allowed to short circuit that and add additional notional loads, or we're allowed to take tau explicitly. If we take tau equal to 1, we use an additional notional load of 0.3% instead of 0.2%. We go through, do our second order analysis, and then when we're done with that, we can use a K factor equal to 1. All right, now it's not my intention to talk about the other methods, but this being a modeling class, it's more appropriate to use either the direct analysis method or the direct analysis method or the effective length method. But if you wanted to go back and use the simplified method of analysis, then you could use these old B1 and B2 factors where we're multiplying the non-translational moments by B1 and the lateral translation moments by B2. The problem with that is that it doesn't account for things like leaning columns. And so that becomes problematic. There's a card that comes with the AISC manual, and it outlines the fourth method, the so-called simplified method. And so with this, you estimate what your story drift is going to be, anywhere from H over 500 to H over 1,000. And based on that and your ratio of the load from step 3, then you can calculate a factor that's applied to all of the bending moments and axial forces. And so this is basically just a watered down version of the effective length. All right, so when you go into a package like visual analysis or SAP 2000, you'll see options. Let me go ahead and launch visual analysis and I'll show you it there. Oh, this version expired. Golly, that's right. I forgot. I didn't update it on this computer. Let me jump into the other computer. That'll take just a minute. Let me close the grade sheet I was looking at so I don't inadvertently show you somebody else's grade. That would get me in trouble. I'm sure there's volumes of paperwork that I would have to fill out for that. All right, so here's visual analysis. When we go into our model filter, our project settings, let's see, where is it? Under the analysis type, you have first order, you have P delta, and you have AISC direct. And so in theory, you can just click that AISC direct type of an analysis, and you've checked, then theory, you checked all of the boxes that AISC would have you do. I would have to caution you about that. That might work just fine. I don't want to say something that's going to get me in trouble with the folks at IES because they give us a great package at no cost, and it does a lot of good things for us. But anytime that you rely on a piece of software to calculate so many things automatically, you're opening yourself up to problems. And so by checking that little option there, you're basically saying that I'm going to trust visual analysis to go through and calculate notional loads, stiffness reduction, and all of these other things, and then do a second order analysis and do all of that right and give me the results. And I lack trust. I have trust issues. Some of those are associated with my personal relationships, but more of them are associated with structural analysis packages that I use. And so when we talk about visual analysis, I would be very reluctant to just check that box and then assume that everything is done correctly. Now, everything is, everything is gray. There's no real black and white. If you're designing a Walmart or something like that, that's probably fine. No big deal. But if you're designing anything more than a 3-4 story structure, then you're probably going to want to be a little bit more diligent in your due diligence. Now, if we go in and look at SAP 2000, that'll take a minute to launch. The associated parameters for direct analysis there are buried a little bit. They're not as obvious as they are in visual analysis. If we go in here, let's see, I don't want to open up your files. Let me open that up instead. All right. So if we go in here and you want to see some evidence of a direct analysis, then it's really when you get into the design options. So if you go into the design tab, which we haven't used at all, and look at some of the options here, they call them preferences or overwrites, then in here you can see the analysis method is AISC direct analysis. And so they include different options there. They make a reference to the direct analysis method, the effective length method, and a limited first order analysis. And so it gives you a description there and talks about the different things that it's going to do. But again, you're asking SAP 2000 to calculate notional loads and apply them correctly. You're asking SAP 2000 to reduce the stiffness of members that are in the lateral force resisting system. And, personally, I would trust SAP a little bit more than visual analysis, but I would want to do a bunch of verification problems before I really gave this my true confidence. And so I'm not going to dive into this with any in any detail, but I wanted to show you where these options are available. And so when you look at homework number 9, when I ask you to include notional loads, you would do that manually by defining different load patterns. And so typically what I do when I do this is I'll define a dead load pattern, and then I'll define an associated notional load pattern along with that. So I define D for dead load, and then I usually define a lowercase n, uppercase d for the notional dead load. Then I do live load L, and then n sub L as the notional live load. I do snow load S, and then n sub S as and so then what you can do is you can go in, and if you define all of those in your load patterns. So I would go in here and I would define another one, call it n sub d, leave it as a dead load type. And then when you go in and define your load combinations, then it's automatically assigned the proper load factor, 1.2 in load combination number 2, for example. But wait a minute, didn't I just say you're not allowed to use load combinations with second order analyses? You have to define the load patterns. You have to define the load factors as a load case instead of a load combination. Well, that's true. So what you can do though is go in here and add the default design load combinations for steel design, and then you can convert those to nonlinear cases. So these are all load combinations. So this is for steel design, that's if we go in and modify that, that gives us 1.2 times dead plus 1.2 times a curtain wall plus 1.5 times snow, right? It included the notional dead load in there, but these are going to be a combination of results of individual analyses. What you can do is you can actually convert those to nonlinear cases. Let me go in and show you what gotta cancel out of that, I guess. I'll go in and show you the load cases that we have. These are all linear static load cases. So what you can do is go back to the load combinations and you can convert those. Let me go ahead and just select all of them. And did it work? Go back to load cases. It didn't work. Maybe I got to select them. Right. There we go. So I'll select all of those, hit OK. And so now if we go back and look at our load cases, then what you'll see are each one of these have been converted to a nonlinear load case. So let me modify that. And so what it does is a P delta analysis with a nonlinear type, and now it has all of those load factors applied here as a case. So all of the loads are applied during the analysis instead of doing a linear combination of the results. And so SAP 2000 recognizes the limitations of the load combination, so it kind of gives you a button to help you do the right thing and put all the loads on before you do the analysis. All right, that brings us to 125, close enough to the end that I'll just go ahead and call it here. When we get back together on Thursday, I'll show you a little bit about SAP 2000 staged construction analysis. Maybe I'll do a half an hour of that and a half an hour showing you how to do a buckling analysis or a modal analysis or something like that. There's a whole lot more to this. We just, in only 14 weeks and a couple hours a week, we just don't have enough time to dig in that deep. So. All right. Yeah, like I said, I'll post the recording of this video relatively soon. It takes an hour to process, and so maybe I'll come back later this afternoon and post that. And then you can go through and look at the solution to the exam that we covered at the beginning. And if you have any questions about your exam grading, you can reach out to me tomorrow during office hours or Thursday morning during office hours. All right, I'll hang around for a minute or two to answer questions, but otherwise I'll see you either in office hours or on Thursday at 12:30 in our next class. All right, thanks a lot.